Welcome to the next video in our area series as we continue exploring notions of area and the principles that are foundational to how we calculate area spaces. Today we're actually going to finally start talking about area in a way that you're going to be more familiar with. In particular, we're going to be investigating today the area of a polygon. Now, in particular, there's some that you're going to be very familiar with. For example, you're likely very familiar with three-sided polygons, triangles, as we've worked with those to a certain degree already. You might also be familiar with other simple polygons, such as rectangles or squares, which are four-sided and are really just types of parallelograms, which we'll see the area is reasonably straightforward for. As we work today, though, we don't want to just talk about finding the area of parallelograms and triangles. We're also going to start investigating more involved figures, such as that of the trapezoid, which is based around similar principles to that of the area of a parallelogram, but has some differences. In our last lesson, we'll start to talk about kites and rhombuses and the area of calculating those. After we've done that, we can talk about the regular polygon, such as a pentagon, or a heptagon, or an octagon, or a nonagon, or a hendecagon, if you even so desire. Now, today, again, we're going to talk about the area of a rectangle, which is probably the way that area was introduced to you in the first place. In fact, it's very likely that your instructor, back when you learned the idea of area for the first time, drew some sort of rectangle on the board, and then managed to break this rectangle up into strips. And they said, look, if I take 4 unit strips down the length, and I take, let's say, 5 unit strips up the width, then it just so happens that the total number of blocks, and I did, of course, a horrible job. Let's say I did 6 and did a good job at that. The total number of blocks is, of course, the product of the length and the width. The two-dimensional space is a product of the two one-dimensional linear spaces. And again, this area is defined precisely because these dimensions exist perpendicular to one another, which is actually a key component of the idea of area. Now, with that said, the area of a rectangle, which we've mentioned as well, is given by the formula area equals base times height, where again, the base and the height are perpendicular measurements in 2 dimensions. And again, we can use this in a very practical way. You'll start to see next week we will have a project for you to begin, which will involve you doing some more practical area calculations. But for instance, we look at a situation like this where it says Hank buys a piece of carpet that measures 40 square yards. Will it cover a rectangular floor that measures these dimensions? And again, what we're going to have to do in this particular situation is determine what the total area is of this rectangular floor. Well, we're going to want to make sure our units are all uniform, so I'm going to get everything in terms of feet, because I know that 13 feet 6 inches is really 13.5 feet. I also know that 21 feet and 6 inches is 21.5 feet, which gives me this situation right here. Now, how do we calculate the area? Well, very simply, we're going to take the width and the length, or the base and the height, however we want to use that language, and create a product of those two things. And in multiplying them together, we're going to figure out the total area. Now, one thing that I notice right now is that my other measurement, before I go any further, 40 square yards, is not in terms of feet. Now, this is going to be something that I want to be very careful about. Because if I go to set up a conversion to get this from square yards into square feet, I'm going to need to be very, very careful. Because if I were to go to set up a proportion, for example, which would be a very handy tool to change my units, I would have to say something like this. Every 1 yard is 3 feet. So 40 yards squared, maybe, is how many feet squared? But you'll notice there's an issue here, and this goes back to what we talked about earlier when we were in our similarity unit. We have a dimensional mismatch. These units over here are calculating two-dimensional measurements. They're in terms of area, in terms of units squared. These units over here are linear measurements. They're just in yards and feet. And so actually, this is not truly an equal proportion yet. Because again, I need to make sure this is also in units squared. So if I'm going to do a conversion, I'm going to get that every 1 yard squared is 9 feet squared. So 40 yards squared is how many feet squared? Go ahead and cross multiply to solve that proportion, and what I'm going to find is that this is really 360 feet squared of carpet. Great. Now, what we're going to find if we multiply these two values together, and again, I don't have my calculator pulled up because shame on me, but the nice thing is I know just from estimation that this will be close to around, let's say, 290-ish, 300-ish. So actually, we are going to be on the lower end of this, thankfully. So it does so happen that this is enough carpet to cover that particular floor. So again, the biggest twist here is the idea that area is often very contextualized. There's often units involved, and while you may be familiar with finding basic area processes, it's really important that you're also aware of the situations in which you need to make sure to use your skills of converting units or getting things into the correct dimensionality as you set up a proportion, such as over here, in order to let you be successful with the more basic area problem and the calculation that you're doing. Now, what about a situation that maybe you haven't seen as often, such as an abstract representation of the area of a rectangle? Well, the way that we can tackle this is a situation like this. Someone tells us the area of a rectangle. It's 90 centimeters squared. And the length is three more than twice the width. So what are the dimensions? Well, notice here everything is measured abstractly. We know that area comes from base times height, or length times width. In this case, it seems to be based on the language of this problem. But here's the problem that we run into in this problem. The situation that we must grapple with is the idea that this length is 3 more than twice the width. Well, what does that mean? What it means is that everything is measured abstractly, and it's measured in relationship to the width. The width is the variable that we want to remain constant in this problem. We want to leave W in there just like anything else. So how would we represent the length as 3 more than twice the width? Well, let's come off to the side for a second. And let's think about this literally. So length equals. So how do I say 3 more than? Well, 3 more than is a direct sum. 3 plus some other amount, 3 more than, and twice the width, 2W. What does that mean? Well, what it means is that this right here is a perfect representation of the length in terms of the width. And once I have these represented abstractly, I can now substitute the length out in order to put in its measurement relative to the width. This will give me only one variable and allow me to solve an area problem just like I would any other kind of area problem. In fact, at this point, I also know the area is 90, so really my equation would look like this. 90 is going to be 3 plus 2W times W. And you'll notice this is where we're going to start seeing what I mentioned earlier, which is this idea that sometimes we're going to have quadratic equations when we calculate area. I get 90 equals, and then I distribute my W through. 3W plus 2W squared. At this point, I might subtract 90 from both sides, and in fact, that would be advisable. So I get 0 equals 2W squared plus 3W minus 90. And at this point, I'm going to need to do some work because I am going to need to try to find some factors that will allow me to break apart this quadratic expression, or equation, excuse me. And so what I might do is I might start the factoring process. Now this is going to be somewhat involved for this one, I believe, because it looks like these are some messy numbers. But again, I'm going to look at the leading term and say, what are the ways that I can deconstruct, break apart, and factor the term 2W squared? And the way I'm going to do that is I'm going to break it apart into its only possible factorization, 2W and W. Now I'm going to look at the end here at negative 90. And I'm going to try to identify the factors of negative 90. In particular, those that are moderately close together, such that I can try to find that middle term of 3W. So I might start listing my factors. I might say 2 and 45 is probably a little extreme. 1 and 90 is obviously very extreme. I have 3 and I have 30. I have 5 and I have 18. And then I have, let's see, 6 and 15. What else do I have? I also have, not 7, 9 and 10, of course. So now what I'm going to do is I'm going to say which of these factors would allow me to have a middle term of 3w. But again, we'll notice that, unfortunately, none of these factors have a difference of 3. And that seems problematic until we recall one important feature, which is whatever term we place at the end here is going to get multiplied by this 2w. So really, I'm trying to identify a set of terms, one of which I double, and one which I keep the same, that then have a difference of 3. And you'll notice that works for this case right here. If I double 6, and then I combine it with a 15, I'll have the difference of 3, so long as I have a positive 15 and a negative 6. Great. What does this mean? Well, again, if we were in Algebra 2, we would then investigate where each of these values equals 0. We would say, look, I have two numbers that multiply to be 0, which means one of them must be 0. And so we would set each of these equal to 0, which I'll come over to the side here and do. We would say 2w plus 15 equals 0. But when we solve that equation, we're going to get w equals negative 15 halves. And while that's a great solution for algebra, for geometry, that doesn't make a lot of sense. To say the width is negative 7.5 units long, that seems really nonsensical. What that means is that this solution is not one of our principal roots. It's not a solution that is positive, really, or just non-negative. So from our other factor, though, we get that the width must be 6. And if the width must be 6, that means that, again, we can take this and plug it back into our original expression for length, doubling the width, making it 12, and being 3 more than that, making it 15. And thus, we now have the length and width of the rectangle that would generate 90 units of area, given those relative measurements to one another between the length and the width. Great. Thanks for hanging in there with me. I hope that made some sense to you. Now, here's the good news. You've mostly been taught about rectangles as being the main principle for area. But the reality is actually that a parallelogram indeed also has the same calculation for area because of one particular feature. The area of a parallelogram is also given A equals B times H, and it's precisely because if you look at a parallelogram, and I'm going to use this image on the left, there is essentially a spot, a corner, where we could draw in, if we wanted to, a perpendicular measurement of height. And what's interesting is that the triangle that is cut off from that main figure could actually be separated and reattached on the other side. Now, this works out because these sides are parallel, which means they end up being a perfect match when we slide it over. Same for these. But all that to say, what that means is that a rectangle and a parallelogram are very closely related, as you might suspect, because again, a rectangle is a type of parallelogram. And what that means is actually the area of a parallelogram is really the same as the area of a rectangle. All we need to do is determine a measurement of height perpendicular to some measurement of a base. Now, if you look at a situation like this, what you'll notice is we're actually in good shapes. If this is truly a parallelogram, right here we have a measure of height. It is from one edge to another edge, and it is perpendicular to both. It's perpendicular to both because, again, these lines are parallel, and it's perpendicular to one of them. Now, what that means is that I can take my height multiplied by the measurement of the length of the base, which in this case is 8 units. So what that means is I can take 8 times 10.5, and I can get 84 as the total area of this particular parallelogram, which is very handy. Again, I could find other measures of height, such as this of the triangle over here, by doing some Pythagorean theorem or some other workings around, and then I could say the base of 12 times whatever this height is. But that's a lot more work than you really have to do, and thankfully, we can find any measurement of height so long as we know the base it's perpendicular to. Again, this can be done abstractly as well. Now, here's the reality. This example over here is almost exactly the same as the example above. So instead of taking more time in order to do a similar process, I'm merely going to set it up and leave it there for you to investigate if you would like. Again, notice as we read, we realize that this is a situation in which the length and width are measured abstractly and in relationship to one another, because as we read, we see the base is 4 more than 3 times the height. Okay, well, what does that mean? Well, that means the base equals 4 more than, so 4 units greater than, 4 plus, 3 times the height, 3h. And we know that the area of a rectangle is base times height. So that means this 95 units, which is the area of the rectangle, is the base, which is 4 plus 3h, times the height of h. Again, exactly like the situation above, we would distribute that term of h to each term in the 4 plus 3h binomial. Then we would get it equal to 0, factor it, and solve for each of the zeros. Again, throwing out solutions that are negative for the case of geometry. Great. Now the triangle is another one you were introduced to that's probably not too surprising. The area of a triangle is really given by the similar formula, which is area is 1/2 base times height. And the notion for the area of a triangle comes precisely from the fact that a triangle is truly just a parallelogram that has been sliced down one of its diagonals, meaning that it has half of the enclosed space that it would if it had the mirror image of itself on the other side making a parallelogram. Now, what that means as well is that finding the area of a triangle is also easy peasy. What we generally need to do is we need to find a measurement of height perpendicular to some sort of base. Now you'll notice in this particular problem here, it looks like it's going to be really complicated and that we're going to need to find this height right here. But the reality is we don't actually have to do that. Again, we need to find a base and a height perpendicular. You'll notice this 40 units here is directly perpendicular with this 30 units here, which means that those can operate as a base and a height for that particular figure, meaning that the area of the triangle, is going to be 1/2 30 times 40, or 600 units squared. Great, nothing too terrifying there, and probably nothing too terribly new. The thing that might be new to you is what we're going to see on the next page, which is our last type of figure to talk about area regarding, and that's that of the trapezoid. Now, before I write down the formula, I'm actually going to write it without variables, and I'm going to write it like this. So I'm going to say, I'll give you both. So the most helpful way that I think of the area is that area is average B times H. The reason I like writing the area formula like this, and you'll see in just a second where that comes from, is because, again, it allows me to relate the idea of area back to the original formula of base times height. Because what you'll notice with a trapezoid, if you look at it very closely, is that a trapezoid really is just a rectangle with two triangles attached on the edges. And in fact, the interesting thing about this is that we can actually take the triangles and split those in half. And the sections that we cut off will attach at the tops, which means that as we slice these triangular wings in half and attach them back up on the other side, we construct a rectangle from the trapezoid. Now, the only problem we face, and the thing that we have to realize, is what happens to the base and the height in these situations. Now, obviously, if I'm doing this process of cutting up my trapezoid and reattaching, the height here stays constant. Nothing changes about my height. My height is fixed. However, what are we doing when we go about splitting this particular bottom base in half and over here, this bottom base in half in regards to the triangle sections? Well, what's happening is we are actually trying to find the halfway point between the distance of this side and the distance to this side, which means what we're actually doing when we're kind of remapping this triangular wing to be a rectangle or part of a rectangle is we are actually calculating and determining what the average distance would be if both this small base and this longer base were to be fixed to be the same base length when we actually have a rectangle. So what that means is that another expression for the area of a trapezoid can be written like this. Area is base 1 plus base 2 divided by 2, which is an average, times our height, which stays constant no matter whether we're talking about a trapezoid or we're talking about a parallelogram. Now, notice this formula allows us to be very flexible, and we can actually calculate and find what heights must be or bases must be given some limited information. And generally, here's what I like to do. So what I like to do personally is I take my area formula and I, again, fill in what I know. So I notice the area of a trapezoid is 104 inches squared. So I fill in 104 is, and I also know the height of the trapezoid, which is 8 units. Now, personally, I just put average base right here. Because before I even try to find, which you'll notice this question's asking me to, the length of one of the other bases, I want to know what the average is supposed to be. So what I'm going to do is I'm going to take this and I'm going to divide by 8. What this will do is it'll tell me that the average base is 13. And let's try writing that again, LabTad. The average base is 13. So now I get to ask myself a question. And again, my question is related to the question I was asked, which is if the base of one trapezoid is 6 more than the other, then what is the length of the two bases? Well, what does that mean? That means one base is my small base, and the other is that base plus 6. And I know that the average of these two things was 13. In other words, base plus 6 divided by 2. Their average was 13. Again, I get 2b plus 6 over 2 is 13. So b plus 3 is 13. Thus, b is 10. What that means is that one of my bases is 10 units, and again, the other is 6 units more than that, so base 1 we'll say is 10, and base 2 is, in this case, 16. And that right there is how we can use this idea of an average base in order to work with some more sophisticated problems. You'll notice the trapezoid really is very similar to the parallelogram in so many ways. It's just we need to calculate some measurement of average either at the beginning or at the end in order to figure out what that base would be if it were to be smashed into a rectangle. Thanks so much. This was lesson 2. As you pop on later, we'll talk about the final types of polygons that we're really interested in calculating area for. Thanks so much.